The cosmos is hiding its greatest secret in plain sight. An enigmatic force called dark energy makes up most of our universe, and we have almost no idea what it is. By the end of this journey, you will know the 25 biggest mysteries that define the cosmic dark energy era. We will investigate why the universe is tearing itself apart and question if our most fundamental laws of physics are wrong. What single cosmic question keeps you awake at night? The universe is not just expanding. It is accelerating, racing outward faster and faster with every passing moment. This single discovery, one of the most profound in human history, shattered our cosmic timeline. For decades, the prevailing wisdom was simple. After the Big Bang, the universe ballooned outward, but the collective gravity of all matter, of every galaxy and star, was acting like a cosmic brake, gradually slowing that expansion down. The ultimate cosmic question was whether that gravity would be strong enough to one day pull everything back together in a big crunch, or if the universe would just coast onward, fading into a cold, dark stillness. The answer, when it came, was something no one had predicted. The breakthrough arrived in the late 1990s through the patient observation of distant stellar explosions, supernova. Astronomers used these brilliant events as cosmic mile markers. By measuring how much the light from these supernova was stretched or redshifted on its journey to us, they could calculate how much the universe had expanded since the star exploded. And by looking at very distant, and therefore very ancient, supernova, they could effectively look back in time to measure the expansion rate of the young universe. The data revealed something astonishing. The distant, ancient supernova were fainter than they should have been, meaning they were farther away than anyone had calculated. The only explanation was that the expansion of the universe was not slowing down at all. It was speeding up. Some mysterious, repulsive force was overpowering gravity itself, pushing galaxies apart with ever-increasing strength. This revelation was so shocking, so contrary to all expectations, that the teams who made the discovery spent years checking and rechecking their work for errors. There were none. For this world-altering discovery, the leaders of these research teams were awarded the Nobel Prize in Physics in 2011. The comfortable narrative of a gradually slowing cosmos was gone, replaced by a far more dramatic and puzzling reality. We now live in the era of dark energy, a name we give to whatever it is that drives this relentless acceleration. But naming something is a far cry from understanding it. What is this force that constitutes the majority of our universe and dictates its ultimate fate? That discovery forces us to confront a deeply unsettling reality. We have given this force a name, dark energy, but its true nature is a complete enigma. This is the second great mystery. What exactly is this stuff that makes up nearly 70% of the entire cosmos? The leading candidate is an idea so old that it predates the discovery of the accelerating universe itself. It is the cosmological constant, a concept originally proposed by Albert Einstein and then famously discarded. He introduced it as a sort of mathematical fudge factor, a repulsive energy inherent to the fabric of empty space itself, to force his equations to describe a static, unchanging universe. When the universe was found to be expanding, he called it his greatest blunder. Yet now, it seems he may have been right for the wrong reason. If dark energy is the cosmological constant, it means that the vacuum of space is not truly empty. Instead, every cubic centimeter of nothingness possesses a tiny, constant energy that pushes the universe apart. The problem is, when physicists try to calculate how strong this vacuum energy should be based on quantum theory, Their answer is wrong by a factor of 1 followed by 120 zeros. It is the single worst theoretical prediction in the entire history of science. This staggering failure hints that our understanding of the vacuum, of nothing itself, is profoundly incomplete. The other major contender is a field known as quintessence. Imagine a new, dynamic kind of energy field that permeates all of space, a cosmic cousin to the field that caused the universe's initial inflation. Unlike the static cosmological constant, quintessence could change over time. It could weaken, strengthen, or even flip its effect from repulsive to attractive. This would mean the acceleration of the universe is not a permanent feature, but a phase we are currently passing through. The challenge is that quintessence, by its very nature, is elusive. We have no direct way to detect its presence or measure its properties. It is a ghost in the cosmic machine, whose existence we can only infer by its gravitational effects on the universe's expansion. So we are left with two radically different possibilities. Is dark energy a simple, immutable property of empty space? Or is it a complex, evolving fifth force of nature? The answer dictates the ultimate fate of everything. Is the cosmos destined for a steady, endless expansion? Or could this repulsive force one day vanish, or even reverse? Identifying the fundamental properties of dark energy remains perhaps the greatest unsolved problem in physics, a puzzle whose pieces are scattered across the entire observable universe. This staggering failure of prediction is the third great mystery, the cosmological constant problem. It is a puzzle born from the two most successful theories in all of physics, general relativity and quantum mechanics, and their utter refusal to agree on the most basic question of all: what is the energy of nothing? Quantum mechanics tells us that the vacuum of space is a seething, bubbling froth. Virtual particles pop in and out of existence in a constant, frantic dance. All this activity should endow every tiny fragment of empty space with a colossal amount of energy, a furious power pushing outward. When physicists calculate this vacuum energy, the number they get is unimaginably huge. Now, compare that to the energy we actually observe from dark energy's gentle push, measured by watching the cosmos expand. The observed value is incredibly small, almost zero. The difference between the theoretical prediction and the observed reality is not just a small error. It is a chasm. The number from theory is 10 to the power of 120 times larger than the number we see. That is a 1 followed by 120 zeros. To grasp the sheer scale of this miscalculation, imagine predicting that a single grain of sand would weigh as much as our entire observable universe. Your prediction would still be far more accurate than the quantum field theory calculation for the energy of the vacuum. This is not just a problem, it is a crisis. It screams that we are missing something profound, something that completely changes our understanding of the quantum world or of gravity itself. This leads to the deeply unsettling concept of fine-tuning. Why is the cosmological constant so exquisitely close to zero, but not exactly zero? If it were just slightly larger, that immense repulsive force would have ripped the universe apart before the first stars could ever form. No galaxies, no planets, no life. If it were slightly more negative, acting like an attractive force, the universe would have collapsed back in on itself in a catastrophic big crunch, almost instantly after the Big Bang. For us to exist, the value had to be balanced on a razor's edge. This apparent perfection feels like too much of a coincidence. It forces us to ask, is our universe somehow special? Are we just incredibly, astronomically lucky? Or is there a deeper principle at work? A law of physics we have not yet discovered that naturally forces this energy to be zero. The cosmological constant problem is a ghost in the equations of physics, a silent reminder that our most brilliant theories are still whispering only part of a much larger, much stranger story. This numerical nightmare leads directly to another, perhaps even more perplexing mystery. Right now, at this very moment in cosmic history, the amount of energy in dark matter and the amount of energy in dark energy are almost exactly the same. This is the coincidence problem, and it feels like finding two strangers who just happen to have identical fingerprints. Dark matter and dark energy are supposed to be completely different entities. Dark matter is an invisible, clumpy substance that pulls things together with its gravity, the cosmic glue that holds galaxies in place. Dark energy is a smooth, repulsive force that pushes space itself apart, the cosmic pressure tearing the universe asunder. One is an anchor, the other is a sail, and for most of cosmic history, their influence was wildly unbalanced. In the early universe, dark matter was completely dominant. Its gravity ruled, pulling matter together to form the first galaxies and the vast cosmic web. Dark energy was an insignificant whisper, a trillionth of a trillionth the strength of dark matter. As the universe expanded and matter thinned out, dark matter's influence slowly waned. Dark energy, if it is a cosmological constant, stayed exactly the same. Its push remained steady while the pull of everything else faded away. The crossover point, the moment in time when dark energy's repulsion finally overcame matter's attraction, happened only about 5 billion years ago. And here we are, living in the brief sliver of cosmic time, just a few billion years on either side of this transition, when the two energies are comparable. Why now, from the universe's 14 billion year timeline, this era of balance is a fleeting blink. It seems far too convenient that we, intelligent observers, should emerge just as this cosmic handover is taking place. Is this just a staggering, one in a billion cosmic fluke? Or is it a profound clue that dark matter and dark energy are not independent strangers, but two different manifestations of a single, deeper phenomenon? Perhaps they are connected in a way we do not yet understand, two sides of the same dark coin. This coincidence is a silent siren, calling us to look beyond our current models and question if the very framework of our cosmology is built on a fundamental misunderstanding. This coincidence of timing forces us to confront a terrifying question. What if the current acceleration is not a gentle, steady push, but a prelude to something infinitely more violent? The fifth mystery is the ultimate fate of the cosmos, and one possibility is so destructive it bears a name that sounds like a final judgment: the Big Rip. Imagine dark energy is not the passive cosmological constant we have assumed, but a force that grows stronger over time. This is a form of phantom dark energy, an entity whose repulsive power does not remain constant but actually intensifies as the universe expands. In this scenario, the acceleration we see today is just the beginning. Billions of years from now, as the universe continues to grow, this phantom energy would become exponentially more powerful. Its push would first overcome the gravitational glue holding clusters of galaxies together. These vast islands of stars would be flung apart into the deepening void. But the horror would not stop there. As the force strengthens, it would eventually target individual galaxies. The Milky Way would be shredded, its stars scattered like dust in a hurricane. Next, the phantom energy would set its sights on solar systems. The sun's gravitational hold on Earth would be broken, and our planet would be hurled into the endless, dark intergalactic space. Still, the rip continues. As the force grows to an infinite magnitude, it would attack the bonds holding planets and stars together. Earth itself would be torn asunder, mountains, rocks, and molecules pulled apart in an instant. In the final, unimaginable moments, the very fabric of spacetime itself would be ripped to pieces. Atoms, nuclei, and even the fundamental particles that make up all matter would be shredded. The universe would end not with a crunch or a fade, but with a catastrophic, instantaneous disintegration of reality itself. For this apocalyptic finale to occur, the phantom energy must have a specific and slightly spooky property where its pressure becomes increasingly negative. Our current measurements are not precise enough to rule this out. We are left staring into the future, wondering if the dark energy we are measuring today is a gentle breeze or the first quiet sigh of a coming storm that will one day tear everything we know into nothingness. This terrifying vision of a big rip forces a radical question. What if we are completely wrong about the cause of the universe's acceleration? Could dark energy itself be a grand illusion, a cosmic mirage born from our own flawed perspective? This is the sixth mystery, and it challenges the very foundation of our cosmic understanding. Perhaps the force we call dark energy is not a real substance at all, but a misinterpretation of the data. One compelling idea is that our universe is not uniform, not a perfectly smooth soup of matter and energy. Instead, it might be lumpy, filled with vast, empty voids and dense walls of galaxies on scales so immense we have not yet mapped them. We live inside one of those dense regions, a cosmic metropolis. From our privileged position, when we look out at distant supernova, their light travels through these colossal voids. The emptiness of these voids affects the passage of light and the apparent expansion rate in ways general relativity predicts, but we might be misreading. The acceleration we measure could be a local effect, a trick of the light caused by our position in a giant cosmic bubble. The entire universe might not be accelerating at all. We might just be living in a special place that makes it look that way. Another, even more profound, possibility is that Einstein's theory of general relativity, the cornerstone of modern cosmology, is incomplete. For a century, his equations have passed every test with flying colors, from the bending of starlight to the precise orbits of planets. But what if gravity itself behaves differently on the scale of the entire observable universe? What if the rules change when you are measuring across billions of light years? Modified Newtonian dynamics, or MEND, was proposed to explain the strange rotation of galaxies without invoking dark matter. Now, some theorists are developing relativistic versions of these ideas, new theories of gravity that do away with both dark matter and dark energy. In these models, the observed cosmic acceleration emerges naturally from the modified equations, without needing any mysterious repulsive energy. The acceleration is not driven by a force, but is a signature of gravity itself weakening in a new way over cosmic distances. This would mean our entire standard model of cosmology, built on general relativity and dark energy, is a beautiful, intricate description of a reality that does not exist. We would be like ancient astronomers constructing complex epicycles to explain the motions of planets, never realizing a simpler truth, that the sun was at the center all along. So we are left with two deeply unsettling alternatives. Either the universe is dominated by a bizarre, repulsive energy we cannot explain, or our theory of gravity, one of humanity's greatest intellectual achievements, is fundamentally wrong. Both possibilities are revolutionary. One requires us to accept a mysterious force that makes up most of reality. The other demands we tear down a pillar of modern physics and start anew. The choice between a universe filled with phantom energy and one where our grasp of gravity is an illusion is a dilemma that defines the frontier of cosmology today. This growing conflict over the universe's fate has a precise, measurable heartbeat, and right now, it is beating out of rhythm. Astronomers call it the Hubble tension, a stubborn discrepancy in one of the most fundamental numbers in all of cosmology, the Hubble constant. This constant is the current expansion rate of the universe, the speed at which galaxies are flying away from us for every million parsecs of distance. Knowing this number is like having the cosmic speedometer for the entire universe. For decades, we have had two primary ways to measure it. The first method looks at the local, modern universe. We observe pulsating stars called Cepheid variables and brilliant supernovae in nearby galaxies, using them as standard candles to gauge distances and recession speeds with incredible precision. This gives us one very firm, very confident number for how fast the universe is expanding right now. The second method looks back to the universe's infancy. We use the afterglow of the Big Bang, the cosmic microwave background, as a fossilized snapshot. By meticulously measuring the tiny ripples in this ancient light, we can run the cosmic film backwards, using our well-tested model of the universe to predict what the expansion rate should be today. These two methods are the bedrock of modern cosmology, and they should agree. They do not. The local measurement says the universe is expanding significantly faster than the pristine early universe data predicts. The difference is not a small, negligible error. It is a persistent, statistically significant gap that has only grown stronger with more precise observations. This is more than a minor calibration issue. It is a direct challenge to our standard cosmological model. The very same model that tells us dark energy makes up 68% of the cosmos. If both measurements are correct, then something is missing from our model. Perhaps dark energy is not a simple cosmological constant, but is evolving, becoming stronger over time. Maybe there is a new, unknown type of neutrino or another relativistic particle streaming through the cosmos, subtly altering the expansion history. Or perhaps this is the first tangible crack in our understanding of gravity and spacetime, a sign that the laws of physics themselves were different in the early universe. The Hubble tension is a quiet alarm bell ringing from the depths of our data, a clue that the dark energy era may be even stranger and more complex than we have so far dared to imagine. This numerical nightmare in our equations points to a deeper, more fundamental layer of reality. The quantum vacuum is not a serene, empty stage upon which the cosmic drama unfolds. It is the stage, and it is alive with a frantic, seething energy. According to quantum field theory, what we call empty space is a turbulent sea of virtual particles. These are not particles in the ordinary sense. They are fluctuations in the underlying fields of the universe, pairs of particles and antiparticles that borrow energy from the vacuum for an impossibly brief moment, only to annihilate each other and return that energy before the universe can notice the debt. This process of creation and destruction happens everywhere all the time, in every single cubic centimeter of space. It is a continuous, foaming frenzy of existence and non-existence. This relentless activity means the vacuum is not nothing. It possesses a real, measurable energy density, a background hum to the cosmos. This is vacuum energy. And for a long time, physicists have wondered if this intrinsic energy of space itself could be the mysterious dark energy driving the universe apart. It is an elegant idea, connecting the impossibly small world of quantum mechanics to the grandest scale of the cosmos. If the quantum vacuum has a positive energy density, then according to Einstein's equations, it must produce a repulsive gravitational effect. It would push, not pull. This would make the cosmological constant a simple, natural consequence of the quantum nature of reality. The problem, once again, is the number. When we calculate how much energy this quantum frenzy should contribute, the result is catastrophically large. The virtual particles popping in and out of existence should be generating a repulsive force so powerful that it would have ripped apart every atom, every nucleus, in the first instant after the Big Bang. The universe as we know it could never have formed. Yet, when we look out at the cosmos, we see a dark energy effect that is incredibly, delicately small. It is as if the universe has somehow canceled out almost all of this vacuum energy, leaving behind only the faintest whisper, a ghost of a push that is only now becoming dominant. This is the heart of the mystery. Is dark energy the quantum vacuum itself? And if so, why is its effect so unimaginably weaker than our best physics says it should be? What unknown principle or symmetry in nature almost perfectly, but not entirely, cancels this energy out? The answer may lie in a theory that successfully unites gravity with quantum mechanics. A theory of quantum gravity that remains our most elusive goal. Until we can peer into that seething vacuum and understand its true nature, the question of whether dark energy is the hum of nothingness will remain one of the most profound puzzles in science. That faint whisper of dark energy we measure today could be a lie. Its gentle push might be a mask, hiding a truly monstrous force waiting in the wings. This is the terrifying possibility of phantom energy, a hypothetical form of dark energy so potent it could tear the universe to shreds in a finite, and perhaps not so distant future. The key to its destructive power lies in a number called the equation of state, represented by the letter W. For the simple cosmological constant, this number is exactly -1. It is a steady, unchanging pressure. But if dark energy is something more dynamic, like quintessence, this number could be different. Phantom energy is the version where W is less than -1. It is a subtle change in the math, but its consequences are apocalyptic. Unlike the constant, phantom energy grows stronger as the universe expands. Its density increases over time, creating a terrifying feedback loop. More expansion leads to stronger phantom energy, which causes faster expansion, which makes the phantom energy stronger still. This runaway effect leads directly to the Big Rip. Current observations have not ruled this out. Our best measurements of the equation of state are still uncertain enough to allow for this phantom possibility. If it is real, the end would not come in some infinitely far-off era. Depending on how much less than -1 the value truly is, the Big Rip could occur in as little as 22 billion years from now. While that may sound like a long time, on a cosmic scale, it is shockingly soon. Our sun will have died long before, but the universe itself would still be relatively young. Its galaxies still bright with middle-aged stars. The end would begin when the phantom energy's repulsive force overwhelms the gravity binding our local supercluster of galaxies. Then, a few million years before the final rip, our own Milky Way would be torn from its neighbors. With just months to go, the solar system would be flung apart. In the final minutes, Earth and the Sun would be ripped to pieces. In the last unimaginable instant, the phantom energy would achieve infinite density. It would tear apart the very fabric of space-time, shredding atoms, nuclei, and the fundamental particles of matter themselves, the universe would cease to exist in any recognizable form. This is not a slow heat death, but a violent, catastrophic, and total disintegration of reality. The search for phantom energy is now a key driver of major astronomical projects. By measuring the expansion history with even greater precision, by mapping billions of galaxies, we are essentially taking the universe's blood pressure, looking for any sign that its cosmic heartbeat is quickening toward a fatal crescendo. The question hanging over us all is whether the dark energy we live with is a benign presence or a phantom slowly awakening from its slumber. Our struggle to explain the value of dark energy might be a profound clue that our universe is not alone. This leads us to the 10th mystery, a concept that pushes the very boundaries of science, the multiverse, the cosmological constant problem. That staggering mismatch between prediction and reality feels like a cosmic error message. Why is the energy of empty space so perfectly tuned for life? One controversial answer is that it is not tuned at all. We just happen to live in one of the rare universes where it is. Imagine a vast, eternal cosmic landscape, an infinite froth of bubbling spacetime where new universes are constantly budding off, each with its own unique, random set of physical laws and constants. In most of these universes, the cosmological constant is enormous. Those worlds are born and then immediately torn apart in a violent inflationary snap, or they collapse back into nothingness before even a single atom can form. They are stillborn cosmos, but in an unimaginably vast ensemble of universes, purely by random chance, a few will have a cosmological constant that is very, very small. In those rare, stable islands, galaxies can form, stars can ignite, and planets can coalesce. Life and ultimately conscious observers like us can emerge. We find ourselves in a universe with a tiny, positive dark energy, not because of any fundamental law, but simply because we could not exist anywhere else. This is the anthropic principle applied on a cosmic scale. It is a statistical explanation for our fine-tuned existence. We are not special, we are just lucky. We are living in the one neighborhood in the infinite multiverse where the conditions are just right for us to be here to talk about it. For some scientists, this is a compelling, even elegant, solution to the fine-tuning problem. It exchanges a mystery of physics for a principle of statistics. For others, it is a philosophical retreat, an untestable idea that effectively ends the search for a deeper, more fundamental reason. If the multiverse is real, then the quest to explain why our constants have the values they do is as futile as a single fish in a vast ocean wondering why it was born in water and not on land. The water is all it can ever know. The multiverse remains one of the most divisive ideas in cosmology. It offers a potential answer, but in doing so, it challenges the very nature of scientific inquiry. Can an idea that posits realities forever beyond our observation ever be considered science? The search for dark energy has led us here, to the edge of physics, staring into the possibility of an infinite cosmic ocean where our universe is just one fleeting bubble among countless others. Even the faint echoes of the universe's birth are telling us a different story. A phantom imprint from the dawn of time, a cosmic measuring stick known as the sound horizon, is not matching up with the structures we see today. This is the 11th mystery. In the first 400,000 years after the Big Bang, the universe was a seething, opaque plasma, a dense soup of particles and light. In this hot fluid, pressure waves raced outward from every tiny density fluctuation, much like sound waves moving through air. These were literal ripples in the fabric of the young cosmos. Then, in an event called recombination, the universe cooled enough for atoms to form, suddenly making space transparent. The light from that moment, released from its prison, streams to us today as the cosmic microwave background. But those sound waves were frozen in place at that exact instant, leaving a permanent, ghostly signature in the distribution of matter. The distance those waves traveled before the universe became transparent gives us a standard ruler. We can see this ruler etched into the CMB with incredible precision, a specific scale of about 500 million light years. This same ruler should then be stamped on the large-scale structure of the universe, visible in the clustering of billions of galaxies seen in vast maps of the sky. When we compare the size of this ruler from the infant universe to its size measured in the adult universe, they disagree. The galaxy maps suggest a sound horizon that is subtly, but persistently, smaller than the one we see in the ancient light. This is the sound horizon anomaly. It is as if a fossilized footprint of a dinosaur does not match the skeleton we dig up. The two should be from the same creature, but they tell different stories. This discrepancy could be a crucial clue that dark energy is not the simple constant we assume. If dark energy were evolving, changing in strength over cosmic time, it would have altered the expansion history of the universe in a way that could precisely create this mismatch. An early burst of extra dark energy could have modified how those ancient sound waves propagated, or a later change could have stretched the galactic structures differently. This anomaly whispers that the dark energy era may not be a single steady chapter, but a story with its own plot twists and turns, a force that is far more dynamic than our simplest models allow. Those phantom whispers from the universe's infancy force a direct and urgent question. Is the strength of dark energy changing? The 12th mystery confronts our most basic assumption, that this force is a simple, unchanging constant. The possibility that it is evolving, growing stronger or weaker over billions of years, would completely rewrite the cosmic forecast. Astronomers are now hunting for this change by measuring a crucial number, the equation of state. Think of this number as dark energy's identity card. For a pure cosmological constant, this number is exactly -1, a fixed setting for all of time. But if dark energy is something like quintessence, a dynamic field, then this number could be different. It might have been -1.1 in the past and be -0.9 today. A value drifting further into the negative would signal phantom energy and a future big rip. A value creeping towards 0 would mean dark energy is fading, its repulsive grip on the cosmos slowly loosening. Finding this number, and any trace of its drift, is the primary goal of the most ambitious astronomical projects of our generation. The Dark Energy Survey meticulously charted the positions of hundreds of millions of galaxies. The recently launched Euclid Space Telescope is creating a colossal three-dimensional map of the universe, measuring the shapes and distances of billions of galaxies across 10 billion years of cosmic history. And the upcoming Vera C. Rubin Observatory will scan the entire visible sky every few nights, discovering countless supernovae to trace the expansion history with unprecedented precision. These telescopes are not just taking pictures. They are building a cosmic speedometer that tracks the universe's acceleration across billions of years. By comparing how fast the universe was expanding then to how fast it is expanding now, we can see if dark energy's foot has pressed harder on the pedal. The data from these missions will shrink the error bars on that crucial equation of state, tightening the constraints until we know, with definitive certainty, whether the force shaping our fate is a steady presence or a shape-shifting phantom? The answer will tell us if the universe is destined for a quiet, endless expansion, or if we are merely in the calm before a storm of cosmic disintegration. But what if our entire cosmic neighborhood is a ghost town? This is the unsettling premise behind the 13th mystery, the void phenomenon. Our most fundamental assumption in cosmology is the Copernican principle, the idea that we do not occupy a special place in the universe. We assume that on the largest scales, the cosmos is smooth and uniform, a homogeneous soup of galaxies. But what if that is not true? What if the Milky Way resides inside a colossal cosmic void, a bubble of relative emptiness spanning billions of light years? From our vantage point deep inside this underdense region, the universe would not look the same in all directions. The local geometry of space would be warped by the lack of mass around us. When we look out at distant supernovae, their light would have to travel through this void and then into the denser walls of the cosmic web beyond. The emptiness of our local bubble would affect the passage of that light in a way that could perfectly mimic the signature of an accelerating universe. General relativity predicts that light gains energy as it falls into a gravitational well and loses energy as it climbs out. Inside our hypothetical void, there is less gravity holding space together, so space itself expands faster here relative to the denser outside regions. A supernova in the distant, denser universe would appear fainter to us because its light loses extra energy struggling to climb out of the deep gravitational well of its home region, and then gains less energy than expected falling into our shallow void. This would make it seem farther away than it truly is, creating the exact same observational effect we attribute to cosmic acceleration. We would be cosmic hermits, living in a vast and lonely desert, misinterpreting the quiet emptiness around us as a powerful, repulsive force driving the entire cosmos apart. The acceleration would be an illusion, a trick of our lopsided perspective. The challenge is the scale of the void required to produce this effect. It would need to be staggeringly large, perhaps over 1 billion light-years across, making our local galactic neighborhood a true anomaly in the cosmos. While some studies have found tantalizing evidence that we might indeed be living in a modest underdensity, the evidence for a void large enough to explain away all of dark energy remains controversial. This idea forces a profound philosophical choice. Is the universe truly dominated by a mysterious dark energy? Or are we simply living in a very special, very empty part of it? Both possibilities violate our cherished principle of mediocrity. One fills the cosmos with a phantom force, the other places us in a cosmic abyss. The void phenomenon remains a haunting reminder that the greatest illusion of all might be the one woven by the emptiness right outside our door. This vast cosmic void we might inhabit is just one thread in a far grander tapestry. The entire observable universe is structured into an immense cosmic web, a network of glittering galaxy filaments surrounding colossal dark emptiness. This is the largest structure we know, and dark energy holds its future in an invisible grip. For billions of years, gravity was the master architect of this web. Tiny quantum fluctuations from the Big Bang were stretched by inflation into minute density variations. Over eons, gravity amplified these seeds, pulling matter into dense knots where galaxies would form and weaving long, delicate bridges of gas and dark matter between them. Vast, empty bubbles, the cosmic voids, grew in the spaces left behind. This intricate dance of structure formation was a battle between two forces, the relentless pull of gravity and the outward rush of the universe's expansion. For most of cosmic history, gravity was winning, but dark energy has changed the rules of the game. As the universe accelerates, the expansion rate is steadily increasing. This acts like a cosmic drag, a pervasive resistance against gravity's work. Imagine trying to build a sandcastle as the tide is coming in. At first, you can pile the sand high, but as the water rises, your efforts become futile. The incoming waves wash away any new structure before it can properly form. Dark energy is that rising tide on a cosmic scale. It is not ripping apart existing structures like the Big Rip would, but it is slowly and inexorably stifling the growth of new ones. The cosmic web we see today is essentially freezing in place. Galaxies that are not already bound together by gravity will never meet. They are being swept apart by the accelerating expansion, their gravitational whispers lost in the growing void. The great cosmic construction project is grinding to a halt. We are witnessing the universe transition from a dynamic, evolving system to a static, fossilized relic. Billions of years from now, an astronomer in a distant galaxy would look out and see a cosmic web nearly identical to the one we map today, a frozen monument to an era when gravity once reigned. This slow strangulation of cosmic growth is one of the most profound and subtle effects of dark energy, a quiet victory of repulsion over attraction that is permanently etching the final form of the universe. This early dark energy hypothesis proposes a startling twist in the cosmic tale. What if the dark energy we see today is not a new actor on the stage, but a returning one? Theorists suggest that a transient, powerful form of dark energy might have also flooded the universe in its very first moments, a fleeting presence that shaped the infant cosmos before vanishing almost without a trace. This is not the same as the cosmological constant we measure now. Early dark energy would have been a dynamic field, a burst of repulsive power that surged during the first few 100,000 years after the Big Bang, and then faded away as the universe cooled. Its brief reign could solve some of cosmology's most stubborn puzzles. For instance, the sound horizon anomaly, where the ancient universe's standard ruler does not quite match the modern one, could be neatly explained. An early burst of dark energy would have given the universe an extra push during that critical period when sound waves were traveling through the primordial plasma. This extra expansion would have changed the apparent size of that frozen sound wave, making it smaller, which is precisely what our galaxy maps seem to show. It would be like a sudden gust of wind during a race, permanently altering the distance between runners just before the finish line was set. This single idea could also help ease the Hubble tension. By modifying the expansion history of the early universe, early dark energy changes the calibration of our cosmic film reel. When we run the film forward from the cosmic microwave background, a model that includes this early burst predicts a present-day expansion rate that is higher, moving it closer to the value we measure directly in our local universe. It is a cosmic adjustment that makes both sets of data agree, without requiring new physics or a rejection of our fundamental models. The implications are profound. It suggests that the dark energy era is not a single, monolithic chapter in cosmic history. Instead, dark energy may be a recurring phenomenon, an energy that can wax and wane, appearing in different forms at different epochs. The force that is now gently pulling the cosmos apart may have once, long ago, given it a crucial, defining nudge. This transforms dark energy from a simple constant into an active participant in the universe's entire life story, a hidden variable that was there at the beginning and has returned to oversee the end. This cosmic principle of uniformity, that the universe has no preferred direction, is a cornerstone of modern cosmology. Yet a faint, ghostly signal from the dawn of time seems to be pointing a single, accusing finger. This is the 16th mystery, a pattern in the ancient light of creation so unsettling that scientists call it the axis of evil. The cosmic microwave background is our most pristine snapshot of the infant universe, a nearly perfect sea of microwave radiation that fills the entire sky. The tiny temperature fluctuations in this light, seen as a modeled pattern of hot and cold spots, are the seeds of all future structure. According to our fundamental assumptions, these fluctuations should be completely random, scattered across the sky with no preferred orientation or alignment. They should be isotropic, the same in every direction. But when researchers began analyzing the data from powerful space-based telescopes, they noticed something strange. Some of the largest scale fluctuations, the biggest hot and cold spots, appear to be subtly aligned along a specific axis, a single great circle in the sky. It is as if the entire universe has a faint preferred direction, a cosmic north. This alignment is not supposed to be there. It defies the cosmological principle, which states that the universe is homogeneous and isotropic. The provocative name, the axis of evil, reflects just how disturbing this potential discovery is to our standard models. If it is real, and not some statistical fluke or a subtle artifact from our own galaxy's emissions, its implications are staggering. One possibility is that it is a fossil, a scar from the instant before cosmic inflation began. Perhaps the universe was not perfectly symmetrical at its absolute beginning, and this axis is the lingering imprint of its initial structure, a structure that inflation stretched across the entire sky but could not entirely erase. Another, even more radical, idea connects this to dark energy. What if dark energy is not perfectly uniform? What if it has a directional quality, a texture that makes the expansion of the universe slightly different along one axis compared to another? This would mean the force driving cosmic acceleration is not a simple, smooth energy, but something with a complex structure that breaks the symmetry of space itself. The axis of evil remains a subject of intense debate. Its statistical significance is tantalizing but not yet conclusive. Future observatories will map the CMB with even greater sensitivity, searching for the definitive proof of this cosmic alignment. Its existence would force us to redraw our picture of the cosmos, not as a featureless expanse, but as a universe that may, after all, have a preferred direction, subtly guided by the hand of its own dark energy. That faint cosmic axis hints at a deeper crack in our understanding, a fracture that runs all the way down to the fabric of reality itself. This brings us to the 17th mystery, the profound connection between dark energy and the final frontier of physics, the quest for quantum gravity. For over a century, we have been living with two separate rulebooks for the universe. General relativity is the brilliant theory of the very large, describing the graceful curvature of space-time by planets, stars, and galaxies. It is the story of gravity. Quantum mechanics is the equally brilliant, yet bizarre theory of the very small, governing the frantic, probabilistic dance of atoms and particles. Both theories are magnificently successful in their own domains, but they are written in completely different languages, and they fundamentally disagree. When you try to combine them to describe gravity on the scale of a single atom, the mathematics breaks down into nonsense. This is the quantum gravity problem, and dark energy sits at its very heart. The catastrophic failure to calculate the energy of the vacuum, that one followed by 120 zeros, is the most glaring symptom of this disconnect. Quantum mechanics sees a vacuum bubbling with infinite energy, while general relativity, when fed that same number, predicts a universe that should have torn itself apart in a fraction of a second. The reality we observe, with its delicately small dark energy, is caught in the middle of this theoretical war. It is as if we have two witnesses describing the same crime, and their stories are utterly incompatible. To solve the dark energy puzzle, we may need the one thing we have been searching for all along, a unified theory of quantum gravity. This would be a single, coherent framework that describes all forces, from the nuclear glue holding atoms together to the cosmic pull of a black hole. In such a theory, the concept of empty space would be completely reinvented. It might not be a smooth, continuous stage, but something far stranger, perhaps a frothing foam of indivisible spacetime grains, or a woven tapestry of tiny, vibrating strings. In that new picture, the energy of the vacuum might naturally cancel itself out, or be locked into the small, non-lethal value we observe. Dark energy, therefore, is not just a mystery to be solved with bigger telescopes. It is a cosmic signpost, pointing directly toward the next great revolution in physics. It is telling us that until we can speak the combined language of the quantum and the cosmic, the true nature of our accelerating universe will remain just beyond our grasp. The fate of the cosmos may be written in the code of a theory we have not yet deciphered. Our cosmic quest for answers is accelerating as fast as the universe itself, driven by a new generation of eyes on the sky. These are not merely bigger telescopes. They are revolutionary machines engineered to take dark energy's fingerprint with a precision we have never before achieved. The Nancy Grace Roman Space Telescope, set to launch in the next few years, is one such cosmic detective. Its mission is to conduct a survey of staggering breadth, peering back across billions of years of cosmic history. It will not just find distant supernovae. It will find them by the thousands, building a supernova catalog so vast, it will trace the expansion history of the universe with a fine-tipped pen instead of a blurry brush. Simultaneously, the Euclid Space Telescope, already in operation, is creating a colossal three-dimensional map of the cosmos. It will measure the shapes and positions of over 1 billion galaxies, looking for subtle distortions. These distortions are not flaws in the image, they are crucial clues. As light from these distant galaxies travels to us, it is warped by the gravitational pull of dark matter lying in its path. By mapping this cosmic shear with exquisite detail, Euclid will reveal how dark matter has clumped together over time, and how dark energy has worked to pull it apart. Think of it as measuring the tension in the invisible cosmic web, strand by strand. The data from these missions will do more than just refine a number. They will perform a decisive test on the very nature of dark energy. Right now, our models are like a set of master keys, many of which could potentially fit the lock. The cosmological constant is one key, various forms of quintessence are others. The measurements from Roman and Euclid will be so precise that they will snap most of these keys in half, ruling out entire families of theories in one fell swoop. They will tell us, with definitive certainty, whether the equation of state of dark energy has remained locked at -1, or if it has been wandering, changing its strength over the lifetime of the cosmos. This is not incremental progress. It is a winnowing process, a great sifting of possibilities that will leave only the most truthful models standing. We are on the verge of knowing whether the force shaping our fate is simple and constant, or dynamic and unpredictable. The universe's greatest secret is about to be placed under a microscope of unprecedented power. The silent dance between the universe's two greatest phantoms may hold the key to their identity. We have always treated dark matter and dark energy as separate entities, one pulling things together with gravity, the other pushing space itself apart. But what if they are not strangers? What if they are talking to each other? This is the 19th mystery, the possibility of a direct interaction between the two dominant yet invisible components of our cosmos. Imagine dark matter as a reservoir of energy, and dark energy as a force that can slowly drain it. In this speculative theory, the repulsive power of dark energy grows by drawing upon the gravitational essence of dark matter itself. This direct exchange could elegantly solve the profound coincidence problem, the puzzle of why their energy densities are comparable today. It would no longer be a bizarre accident of timing. Instead, it would be a natural consequence of their relationship. As dark matter's density decreased over cosmic time through its interaction with dark energy, the two energies would inevitably cross paths and appear balanced for a brief cosmic moment, which just happens to be now. This idea is not just mathematical elegance. It could explain real, observed anomalies. Some measurements of the shapes and distributions of gigantic galaxy clusters seem slightly off from what our standard models predict. The clusters appear a little less dense, a little more spread out than they should be. An interaction between dark energy and dark matter could account for this. If dark energy is effectively converting dark matter into more of itself, it would weaken dark matter's gravitational grip, preventing the clusters from condensing as tightly as we would expect. We would be seeing the cosmic footprint of this shadowy exchange. Searching for this interaction is like trying to hear a whisper in a hurricane. We cannot see either component directly. We can only look for the subtle, cumulative effects they have on the universe's structure and expansion over billions of years. The next generation of telescopes will scour the cosmic web for any tiny deviation, any statistical quirk in the distribution of galaxies or the growth of the largest structures that could be the telltale signature of this conversation. Finding it would revolutionize cosmology, unifying the two greatest mysteries of the modern era into a single, profound phenomenon. That profound connection to quantum gravity leads us directly to one of the most mathematically beautiful yet frustrating attempts to explain it all. String theory was once hailed as the ultimate theory of everything, a framework where the fundamental particles of the universe are not dots, but unimaginably tiny, vibrating strings. The pitch and vibration of these strings would determine whether they manifest as an electron, a quark, or a particle of light. This elegant idea promised to seamlessly weave general relativity and quantum mechanics into a single, coherent tapestry. Yet when it comes to dark energy, string theory faces a crisis of abundance. The mathematics of the theory do not produce a single, unique universe like our own. Instead, they describe a colossal landscape of possibilities, a cosmic menu with an estimated 10 to the power of 500 different potential versions of reality. Each of these versions corresponds to a different stable configuration of the extra dimensions string theory requires, and each has its own unique value for the cosmological constant. In this vast landscape, there are solutions where the cosmological constant is a huge positive number, universes that blew apart instantly. There are solutions where it is a huge negative number, universes that collapsed immediately. And scattered like rare gems in this cosmic desert, there are solutions where the cosmological constant is a tiny positive number, very much like the one we observe. The multiverse idea finds a natural, if controversial, home here. In this picture, our universe is not special by design, but simply one that randomly ended up with the right small value for life to form. We are a single, successful ticket in a cosmic lottery of unimaginable scale. The challenge, however, is profound. With 10 to the 500 possibilities, string theory risks predicting everything, and therefore predicting nothing. How can we ever test a theory that allows for every possible outcome? The search for a unique fingerprint, a specific prediction that can be checked by observation, remains the theory's greatest hurdle. The string theory landscape is a breathtaking realm of mathematical potential, but it leaves us wondering if the true nature of dark energy is a fundamental physical principle we have yet to grasp, or just a random address in an infinite cosmic metropolis. The vacuum of space is not empty. It is, in fact, a place of immense and frantic activity. This is the 21st mystery, a concept that challenges our deepest intuitions about nothingness. We are taught that a vacuum is the absence of all things, a perfect and serene nothing. But quantum field theory paints a radically different picture. What we call empty space is a seething, bubbling sea of potential. At every single point, pairs of virtual particles and antiparticles are constantly flickering into existence, borrowing energy from the void for a fleeting moment before annihilating each other and vanishing. This is not a metaphorical dance. It is a real, physical process with real consequences. All this frantic activity endows the vacuum with a fundamental energy density, a background hum to the cosmos. This is the zero-point energy of the universe, and it is here that the story takes a bizarre turn. According to Einstein's theory of general relativity, all energy, including the energy of empty space, has a gravitational effect. We are used to thinking that matter and energy create an attractive force, the gravity that pulls things together. But the mathematics of relativity allows for a strange possibility. If a substance has a strong enough negative pressure, like a tension pulling inward, it can generate a repulsive form of gravity. Think of it like this. If you try to stretch a rubber band, it pulls back. That inward pull is a form of negative pressure. Now, imagine that same kind of negative pressure is an intrinsic property of the vacuum itself. The quantum foam, with its constant particle creation and annihilation, is under a kind of cosmic tension. And according to Einstein's equations, this specific type of energy with strong negative pressure does not pull things together. It pushes them apart. The vacuum energy creates a gravitational repulsion. This is the ultimate irony. The same quantum activity that should, by all rights, be generating a colossal attractive force instead produces a gentle but relentless push. The nothingness itself is not passive. It is an active participant in the cosmic drama, and its inherent energy is stretching the very fabric of the universe. So when we look out at the accelerating cosmos, we may not be seeing the effect of some exotic new field. We may be witnessing the gravitational signature of empty space itself, a silent, pervasive force born from the ghostly activity of the quantum void. The same equations that predict the primordial hydrogen and helium so perfectly also forecast a specific amount of lithium. But when astronomers look at the oldest stars in our galaxy, the ones that formed from the pristine gas of the early cosmos, they find only about a third of the lithium that should be there. This is the cosmological lithium problem, a small but persistent crack in our otherwise triumphant story of the Big Bang. For decades, it was seen as a minor puzzle, perhaps a misunderstanding of stellar processes that could destroy lithium. Yet the discrepancy refuses to go away, and its persistence is now a screaming clue. The lithium produced in the first few minutes was forged in a frantic race against time, as the expanding and cooling universe froze the nuclear reactions in place. The final amount is exquisitely sensitive to the expansion rate during those critical first minutes. If the universe had expanded just a tiny bit faster or slower, the final lithium yield would be different. This is where the ghost of dark energy may be stirring. Could an exotic form of energy, a relative of the dark energy we see today, have been active during the universe's first moments? A transient field, similar to the early dark energy proposed to solve the Hubble tension, could have given the expansion rate a slight extra nudge during Big Bang nucleosynthesis. That tiny modification to the cosmic tempo would have been enough to alter the nuclear chain reactions, leaving behind less lithium while leaving the hydrogen and helium untouched. The lithium problem transforms from a minor accounting error into a potential fossil, a relic from an era when a dark, repulsive force first flexed its muscles. It hints that the physics of the vacuum, the rules governing empty space, were not always as passive as they seem today. The missing lithium in the oldest stars might be the cosmic equivalent of a single misplaced thread, suggesting the entire tapestry of the early universe was woven with a darker, more dynamic energy than we ever suspected. Gravitational waves are ripples in the fabric of spacetime itself, and they carry with them a direct measure of cosmic distance. When two massive black holes spiral into each other in a distant galaxy, they shake the universe, sending out these faint tremors that travel for billions of years before reaching our detectors. The beauty of these signals lies in their purity. The amplitude of the gravitational waves tells us the intrinsic loudness of the collision, a property directly tied to the masses of the black holes. By comparing this intrinsic loudness to how faint the signal appears when it finally reaches us, astronomers can calculate the precise distance to the event. It is a cosmic standard siren, a direct shout across the void whose fading volume reveals exactly how far it has traveled. This method is completely independent of the cosmic distance ladder built from Cepheid stars and supernovae. It does not rely on understanding stellar physics or the complex behavior of exploding stars. It relies only on the immutable laws of gravity as described by Einstein. Each black hole merger we detect is a single, precise data point in the vast chart of cosmic expansion. By collecting enough of these events from different epochs, we can trace how the universe has stretched over time, building a new and independent history of its acceleration. This gravitational wave perspective is free from the systematic errors that may have crept into our traditional measurements. It is a clean test, a new witness taking the stand in the trial to understand dark energy. Current observatories like LIGO and Virgo are already making these measurements, but their reach is limited. The future, however, holds incredible promise. The Laser Interferometer Space Antenna, or LISA, a planned space-based observatory, will open up the low-frequency gravitational wave sky. It will hear the mergers of supermassive black holes from the farthest reaches of the cosmos, events so powerful their signals will have been traveling for most of the universe's history. With LISA, we will not just be adding more points to our graph. We will be drawing an entirely new one from scratch, a curve of cosmic expansion written in the language of spacetime ripples. This independent confirmation or contradiction could finally break the deadlock. It will tell us if the dark energy we have been measuring through the light of dying stars is the same force that echoes in the collisions of black holes. The silent universe is beginning to speak to us through its vibrations, and it may soon reveal whether our cosmic acceleration is a fundamental truth or a beautiful, lingering illusion. Our very existence might be the only answer we will ever get. This is the unsettling heart of the 24th mystery, the anthropic principle, a concept that blurs the line between profound science and unprovable philosophy. It confronts the staggering fine-tuning of the cosmological constant head-on. Why is the energy of empty space so perfectly balanced on a razor's edge, allowing for galaxies, stars, and ultimately us? The anthropic principle offers a stark and simple answer. The universe is this way because if it were any different, we would not be here to ask the question. In a cosmos where the cosmological constant was just slightly larger, the repulsive force would have been so violent that it would have ripped apart every proto-galaxy before it could ever form. No stars, no planets, no life. If it were slightly more negative, the universe would have collapsed back in on itself in a fiery big crunch after just a few million years. For conscious observers to evolve, the constants of nature had to fall within an incredibly narrow, life-permitting range. We are not seeing a universe designed for us. We are simply seeing the only kind of universe that could possibly have produced us. This idea finds a natural, if controversial, home in the concept of the multiverse. If an infinite number of universes are constantly bubbling into existence, each with random physical constants, then it is no surprise that we find ourselves in one of the exceedingly rare ones where the numbers just happen to work out. We are the inevitable product of cosmic statistics, living in the one neighborhood where the conditions are just right. For some scientists, this is a powerful and elegant solution to the fine-tuning problem. It transforms a miracle into a mere selection effect. We are not special, we are just lucky. For others, this is a philosophical dead end, a retreat from the traditional goal of science to find fundamental, causal explanations. It risks making cosmology untestable. If we accept that any property of our universe can be explained away by saying it is necessary for our existence, does that not extinguish the drive to look for a deeper, more elegant physical law? The debate rages. Is the anthropic principle a profound insight into the nature of reality, or is it a sophisticated way of giving up? The value of dark energy forces this question upon us, making our own consciousness a central and deeply puzzling part of the cosmic mystery. The universe's greatest secret might be that we are asking the wrong questions entirely. Our entire cosmic narrative, the magnificent story of a Big Bang followed by an accelerating expansion driven by dark energy, rests upon a foundation we assume is solid. But what if that foundation is made of sand? Every single mystery we have explored, from the Hubble tension to the phantom threat of the Big Rip, is a symptom. The disease could be our core belief that we fundamentally understand gravity and the cosmos on its largest scales. We have built an intricate and beautiful model, lambda-cidium, which relies on dark energy and dark matter to make the equations work. It is a masterpiece of modern cosmology, but it is also a house of cards. If one card is pulled, the entire structure could collapse. That final card is general relativity itself. For a century, Einstein's theory has been our unshakable guide, predicting the bending of light and the orbit of Mercury with uncanny precision. But its true test has always been the cosmic scale, the realm of the entire observable universe. Here, we are forced to invent dark components to make its predictions match our observations. This is not necessarily proof that dark energy and dark matter exist. It could be proof that our theory of gravity is incomplete. We are like navigators using a map that is 99% accurate. That last 1% of error seems small, but on a journey across an ocean, it means you will miss your destination by hundreds of miles. Our map of the cosmos, built on general relativity, has brought us far, but the shores we see do not match the chart. Instead of inventing invisible continents and strange seas to explain the discrepancy, perhaps we should question the map's fundamental geometry. New theories of gravity, often called modified gravity, attempt to do just that. They suggest that gravity behaves differently on the scale of galaxies and the cosmic web than it does in our solar system. In these models, the observed acceleration of the universe emerges naturally from the revised equations. There is no need for a mysterious dark energy because the apparent push is just a signature of gravity weakening in a new way across vast, empty voids. The cosmic acceleration becomes an illusion, a misinterpretation of a deeper gravitational truth. This possibility is as humbling as it is exhilarating. It means that everything we think we know about the universe's composition and its ultimate fate could be a grand illusion. Dark energy would not be a substance making up 68% of reality. It would be a placeholder for our ignorance, a label we stuck on a phenomenon we did not comprehend. The 25 mysteries of the dark energy era then converge on a single, staggering point. We are at a crossroads in our understanding of reality, facing a choice between a universe dominated by phantoms or a revolutionary new physics that redefines the force that holds it all together. The true nature of dark energy is not just a puzzle to be solved. It is a doorway, and on the other side lies either a cosmos filled with enigmatic darkness or a fundamental rewriting of the rules of the universe itself. From the accelerating expansion that shattered our cosmic timeline to the ghostly axis that might point toward a preferred direction in the void, these 25 mysteries are not merely gaps in a textbook. They are the bleeding edge of our understanding, the places where our maps of reality turn fuzzy and the real adventure begins. Each one, from the staggering numerical failure of the cosmological constant to the haunting whispers of an interacting dark sector, represents a fundamental question mark placed beside our most cherished theories. They challenge the nature of gravity, the fabric of spacetime, and the very definition of nothingness. This is not a story with a tidy ending. It is an ongoing investigation, a grand cosmic detective story where the clues are written in the light of dying stars, the ripples of colliding black holes, and the faint afterglow of creation itself. The solutions to these puzzles will not just fill in blanks. They will likely rewrite the rules of physics and reveal a universe far stranger and more magnificent than we have ever dreamed. We stand at a pivotal moment, armed with powerful new telescopes and brilliant new ideas, poised to solve the greatest mysteries of the cosmos. The journey is just beginning. Now, we want to hear from you. Which of these 25 mysteries of the dark energy era captivates your imagination the most? Does the terrifying phantom of the Big Rip keep you wondering, or is it the profound fine-tuning that allows for our existence? Share your thoughts in the comments below, and subscribe to join us as we continue to explore the deepest enigmas of the